10.2 Lesson 4, Plane Curves and Parametric Equations. Our objective for today's lesson is you will understand the derivation of parametric equations for a cycloid. So before we do that, we'll take a look at what a cycloid is. And we know what a parameter is, and we'll discuss what we will assign to be the parameter when we're deriving a set of parametric equations for the cycloid. In a motion problem, the parameter might represent time. So for our problem today with the cycloid, what will the parameter represent? That's something that we will talk about. And these are some prior knowledge vocabulary terms that you need, which were a part of the prerequisite worksheet. So our lesson today will have this format. One, we will go over some prerequisite knowledge. Two, I will show you how you can actually make a cycloid so you understand exactly how a cycloid can be made if you have, for example, a roll of tape, which would be like a circle, right? And then you attach a marker to one point on the tape and you roll it around the ground. And that would trace what we call a cycloid. So we'll talk about what a cycloid is, because once you understand that, then you will be able to put these two things together to understand the objective for today, which is how we come up with a set of parametric equations for a cycloid. The first thing that you need to do in that process is to understand what the parameter will represent so that you're clear about what the parameter represents and how you can use that along with the prerequisite knowledge and your understanding of what a cycloid is to come up with a set of parametric equations for a cycloid. So we begin by reviewing some geometry. So prerequisite knowledge, worksheet number 1. So you have two parallel lines that are indicated by these symbols, and they're cut by a transversal. So this is a transversal. So if two parallel lines are cut by a transversal, this is a theorem from geometry, then corresponding pairs of alternate interior angles are congruent. Interior angles are angles that are between the two parallel lines. So they're marked 1, 2, 3, and 4. So we have 4 interior angles. And then when we say alternate interior angles, we're talking about interior angles that are on alternate sides of the transversal. And when we say corresponding pair of alternate interior angles, we're talking about, for example, angle 1 corresponds to angle 2, and angle 3 corresponds to angle 4. So there is a theorem from geometry that tells us that if two parallel lines are cut by a transversal, corresponding pairs of alternate interior angles are congruent. So angle 1 has to be congruent to angle 2, and angle 3 has to be congruent to angle 4. So here we have number 2 from the prerequisite worksheet. So these are the unit circle definitions of the sine and the cosine functions for any angle theta. Sine of theta is the y-coordinate of the point on the circle intercepted by the terminal side of the angle in standard position, and cosine of theta is the x-coordinate of the point on the unit circle intercepted by the terminal side of the angle of rotation when it is in standard position. So because of how these trig functions are defined using the unit circle, you will make this observation. So for example, if you have an angle theta that measures 30 degrees with the positive x-axis, we can write that sine of 30 degrees is equal to the y-coordinate of the point on the circle intercepted by the terminal side of the angle. It's equal to 1/2. But make this observation. If this angle here is also 30 degrees, then the angle of rotation that we have here would be 180 degrees minus 30 degrees, or 150 degrees. Or you can write sine of 180 degrees minus 30 degrees, which is, of course, 150 degrees. But sine of 150 degrees is also 1/2. And that's what this is stating here. Sine of theta is equal to sine of 180 degrees minus theta. And why does that happen? Because both of those angles, their terminal sides, intercept a point on the unit circle having the same y coordinate of 1/2. They're basically at the same height above the horizontal axis. So this is a relationship that's true just by the definition of sine using the unit circle. Now when you look at cosine, for example, if you look at cosine of 30 degrees, cosine of 30 degrees is square root of 3 over 2. So you have square root of 3 over 2. If you look at cosine of 180 degrees minus 30 degrees, you're looking at cosine of 150 degrees, and that would be the opposite of the cosine of 30 degrees. Cosine of 150 degrees is negative square root of 3 over 2. So this relationship will be generally true just because of the definition of cosine using the unit circle. Cosine of an angle of rotation theta is equal to the opposite of the cosine of 180 degrees minus theta. Number 3, we're reviewing some right triangle trigonometry. You may remember the mnemonic device SOHCAHTOA to help you remember the definitions of the trig functions using a right triangle. So if you have a right triangle, you're going to be using one of the two acute angles. So in this right triangle, one acute angle is acute angle APC. So here's the acute angle APC. And sine of an angle is the ratio of the length of the opposite side to the length of the hypotenuse. So from this acute angle APC, the opposite side would be segment AC, and the hypotenuse would be segment PC. So the length of the opposite side is the distance from A to C. The length of the hypotenuse is the distance from P to C. So sine of an acute angle is the ratio of the length of the opposite side to the length of the hypotenuse. And cosine of an acute angle APC, would be the ratio of the length of the adjacent side to the length of the hypotenuse. And the length of the adjacent side would be the length of the segment PA, which I can write as PA or AP. And then the length of the hypotenuse would be PC. So adjacent over hypotenuse. Here's the last thing that you need to understand from our prerequisite worksheet to be able to understand our lesson for today. If you have a circle, let's say circle C, and the circumference of this circle is given by 2 pi r, and because the radius of the circle is given to be a, I know that the circumference of this circle will be 2 pi times the radius. The radius is a. So the circumference of circle C is 2 pi a. So the question is, let's take a look at what we have here. In this circle, we have an arc of the circle. So this is called an arc, a portion of the circumference. We will call this arc PD. The length of arc PD can be found by using this proportion. So this is a proportion. So the length of arc PD is to the circumference as the angle of rotation that forms the arc is to the angle of rotation for the entire circle, which is of course 2 pi. So when you replace arc length with the length of arc PD, the circumference is given by 2 pi times the radius, 2 pi a. The angle of rotation that gives us the arc PD is theta, and the angle of rotation for the full circle is 2 pi. And you can solve this proportion for the length of arc PD by cross multiplying. and simplifying by canceling the common factor of 2 pi. And when you do that, you get that the length of arc PD is simply equal to, the angle of rotation that gives us the arc length, the angle of rotation that gives us the arc, multiplied by the radius of the circle. So the length of the arc PD is the angle of rotation that gives us the arc multiplied by the radius of the circle. So we took care of some prerequisite knowledge that you need, and now we're going to try to understand what a cycloid is by looking at a particular, I actually make a cycloid, and let's look at that video. And then we will move on to number 3, where we will put these two things together to understand the derivation of parametric equations for a cycloid. So to see how I made a cycloid with a roll of tape and a marker attached to a point on the tape, you can click on the link, and that will take you to a separate video that shows how a cycloid is made, and so you will understand what a cycloid is. Now with that, we're now ready to move on to the third part of our lesson for our objective. You will understand the derivation of parametric equations for a cycloid. So from the video that you just saw, a cycloid was made by rolling a tape, and here is the y-axis, just like you see in this diagram, for example 5 from your textbook, and here is the x-axis, just like you see in this diagram, for example 5 from your textbook. And we mentioned what the parameter is going to represent. It's going to represent the angle of rotation for the circle as it is rolling along the x-axis, or in my demonstration, as it was rolling along the floor. And you have this cycloid, which is traced as a result of that motion of the circle by a point on the circle. In my demonstration, that point was, of course, a marker that was attached to my roll of tape. And the objective that we have is to come up with a set of parametric equations in terms of the parameter theta representing the angle of rotation for the circle that will give us the coordinates of a point on our cycloid. So this point will have coordinates x comma y, and we'd like to write x as a function of the parameter theta, and we'd like to write y as a function of the parameter theta, where the parameter theta represents the angle of rotation for the cycloid. So if you look at the diagram in the textbook, you can see that at this point here, the x coordinate would be equal to 2 pi a, because how did we get from the origin to this point? We had to roll our roll of tape one complete revolution, corresponding to an angle of rotation 2 pi radians. And so the length of the arc traced by an angle of rotation that is equal to 2 pi radians would be 2 pi times the radius. And the radius of our circle is a. So that's why we have 2 pi a here. Because when you roll the tape one revolution, it travels a horizontal distance that is equal to the circumference of the tape, which is going to be 2 pi times the radius. And if we let a represent the radius, that circumference of the tape will be 2 pi times a. The horizontal distance traveled by the tape as it moves from the origin to this point is 2 pi a. So that's x. But what we want to do is, okay, so we know it's going to be 2 pi a when theta is equal to 2 pi. But what if we just have theta and it's not equal to 2 pi? It could be anything between 0 and 2 pi, or even greater than 2 pi. So we want to come up with a function of the parameter theta that will give us the x coordinate of any point on this cycloid as a function of the angle of rotation theta. And we want to do the same for the y coordinate. We want to come up with another function, and in terms of theta, and together these will be our parametric equations for our cycloid. And in fact, you already see what they will be, but we're going to talk about how we come up with that. So you see that what the final result will be, but we're going to go through the process of deriving it. So to understand that derivation, you've got to look at the diagram from your textbook for example 5. We're going to use how it's labeled to help us with the derivation. So the circle has a center, and the center of the circle is D. Point D is it's on the circle, so the distance from the center to a point on the circle, that distance would be the radius of the circle, which is A in our setup. So the distance from C to D would be A, representing the radius of the circle. And of course, theta represents the angle of rotation of the circle. It is the parameter in our derivation. And if you look further here, you have triangle APC, and notice that it's a right triangle, and one vertex of the triangle is at the center of the circle. Another vertex of the triangle is on the circle. So the distance from the center of the circle to a point on the circle is, of course, the radius of the circle, which will be A. And you have a third vertex of the circle at point A. And then you have segment AB, which is parallel to segment CD, and it is in fact congruent to segment CD. So the length of segment CD is the radius of the circle, so the length of segment AB is also the radius of the circle. So you've got to understand that. And if you look at our diagram, you've got segment AC, which is one side of the right triangle, and you've got segment BD, which is congruent to that. So whatever the length of segment AC is, the segment BD will have the same length. So those are some things that we need to understand. So now here's the last thing that I would like for you to understand before we look at the details for how we come up with the set of parametric equations we have here. So here's the last thing that you need to understand. You've got x, y, and this is what we're after, right? How can we describe x in terms of the parameter theta? How can we describe y in terms of the parameter theta? That's what we want to focus on right now. So the first thing that we're going to recognize is that x is here. This is x, and you can see that x is the distance from the y-axis to this point. So in other words, because it's the distance from the y-axis to point P, it would be equal to the distance from point O to point B on the x-axis. So x is equal to the distance from the origin to point B on the x-axis. You can also write it this way, and you'll see why we do this. It's equal to the distance from the origin to point D minus the distance from point B to point D. And you'll see why we do this in a moment. And for y is the distance from the x-axis to point P. So you can write y is equal to the distance from point B to point A plus the distance from point A to point P. So if you add those two lengths, you will get the distance from B to P, which is the y coordinate of point P. So we have y is equal to BA plus AP. So now that you understand that, we're ready to look at how we come up with this set of parametric equations to describe the coordinates of points on the cycloid in terms of the parameter theta, which represents the angle of rotation of the circle that is causing the cycloid to be traced. So to complete our problem, we need to write the distance from O to D in terms of the parameter theta, and we need to write the distance from B to D in terms of the parameter theta. We need to find out the distance from B to A in terms of the parameter theta, and the distance from A to P in terms of the parameter theta. Once we have that, we'll be done. Actually, the distance from B to A, we don't really need the parameter theta for that, because the distance from B to A, if you look at our diagram here, the distance from B to A is equal to the distance from D to C. So from A to B is the same as the distance from C to D, which is, of course, the radius of the circle. So we already know that the distance from B to A is just the radius of the circle. So it's just going to be A plus the distance from A to P. We need to write the distance from A to P in terms of the parameter theta. We need to write the distance from O to D in terms of the parameter theta, and the distance from B to D in terms of the parameter theta. So let's take a look at how we do that. So sine of the angle theta, as we saw from our prerequisite worksheet, is equal to sine of 180 degrees minus theta. We saw that from our prerequisite worksheet. And consider this. So we also saw on our prerequisite worksheet that if we have two parallel lines, which I'm sketching in red now, so if we have two parallel lines that are cut by a transversal, and the transversal will be right here, this is our transversal, pairs of alternate interior angles are congruent. So 180 degrees is the angle of, it's a straight angle, so that's what you have here, 180 degrees. The angle of rotation for the circle is theta, which you see here, and 180 degrees minus theta would be this angle right here, 180 degrees minus theta. Now, because of that theorem from geometry, when you have two parallel lines cut by a transversal, pairs of alternate interior angles are congruent. So that means the angle here, which I will try to highlight in maybe black, right here, that would also have a measure of 180 degrees minus theta. And of course, that angle is the angle APC. That's the angle APC from our right triangle. That's the angle APC from our right triangle. So the measure of angle APC is 180 degrees minus theta. So we can make that substitution. And now we can use right triangle trigonometry. How do you find the sine of angle APC? The sine of angle APC using right triangle trigonometry is the length of the opposite side, which would be the distance from A to C, over the length of the hypotenuse, which would be the distance from P to C, but P is on the circle and C is the center of the circle, so the distance from P to C is, in fact, the radius of the circle, which is A. And make the observation that the distance from A to C, looking at this diagram, the distance from A to C is equal to the distance from B to D. So you can replace AC with the distance from B to D and B over DA. So now we can actually solve for BD, because take a look at what we have here. We can write sine of theta is equal to BD over A. Sine of theta, where theta is the parameter representing the angle of rotation of the circle, is equal to BD over A. So what is the distance from B to D? In terms of the parameter theta representing the angle of rotation, it is equal to A, which is the radius of the circle, times sine of the angle of rotation. So with that, I'm able to write my parametric equation for x. Almost. I have BD, but I have to talk about OD. What is OD? It's actually pretty simple. OD is the distance from the origin to this point, corresponding to an angle of rotation for the angle of rotation given by theta. And if you look at number 4 from our prerequisite worksheet, we know that the length of arc PD, which is equal to the distance from O to D, that's how much the circle has rolled. It has revolved by an angle theta, and it has rolled a horizontal distance equal to the length of arc PD, which by number 4 from our prerequisite worksheet is equal to A times the angle of rotation, where A represents the radius of the circle. So in fact, the length of arc PD is equal to the distance from O to D, and that length of arc PD is A times the angle theta. So we're going to replace OD with the length of arc PD, which is equal to A times theta. So with that, I can write X is equal to A times theta minus the length of segment BD, which would be A times sine of theta. And of course, you can just factor out A from each of these two terms, and this will give you exactly what you see here. So now we'll talk about how we can get the parametric equation for y, and we will be done. So again, we refer to the same diagram that we had worked with before, with all of the same labeling, and from our prerequisite worksheet, we know that cosine of theta is equal to the opposite of the cosine of 180 degrees minus theta. And just like we saw with what we did for to get the parametric equation for the x-coordinate, we have the same setup. So we have two parallel lines cut by a transversal, and because of that, this pair of alternate interior angles is congruent, and the measure of the angle here is 180 degrees. The angle of rotation is 30 degrees. The angle of rotation is theta. So 180 degrees minus theta is the angle that we have here. So that would be the alternate interior angle will also have the same measure of 180 degrees minus theta. And that is, of course, the angle APC. But we already saw that earlier, so nothing unusual about that. So this is from our prerequisite worksheet. And for this right triangle APC, cosine of the angle theta, by the analysis that we just went through, is equal to -1 times cosine of angle APC. So cosine of theta is -1 times cosine of angle APC because of the analysis that we just went through, having to do with all of the information from the prerequisite worksheet. So now you can just focus on the right triangle APC. Cosine of angle APC is adjacent over hypotenuse. The length of the adjacent side is the distance from A to P. And the length of the hypotenuse is, of course, A. So where does the negative sign come from? It comes from here. And that has to do with what we saw in the prerequisite worksheet, deriving from the definition of cosine on the unit circle. So basically, we're at this point here, putting all of that together. We have cosine of theta is equal to -AP over A. So now you can solve for AP. Why would we want to do that? Because look at our work from earlier. Y is equal to BA plus AP. And we know BA is equal to the radius of the circle. And now we can write AP in terms of the parameter theta. AP is equal to -A times cosine theta. So now we can write Y is equal to A plus AP plus negative would be minus A times cosine theta. And now we can go ahead and just simplify that a little bit, and we will get Y is equal to A times 1 minus cosine theta when we factor out a from each term. And of course, that's exactly what you see here. Y is equal to a times 1 minus cosine theta. So in this lesson, we derived a set of parametric equations for a point on the cycloid in terms of the parameter theta representing the angle of rotation of the circle. So we derived a set of parametric equations for the coordinates x and y of a point on the cycloid in terms of the parameter theta representing the angle of rotation for the circle.